All right, so welcome in everyone. My name is Brian. We're going to be talking a little bit about the Data Encryption Standard and Feistel Networks in this particular video. Data Encryption Standard is a little bit outdated. We don't use it anymore, although at one point it was considered, I think, the pinnacle of encryption standards.
Oh, yeah? Prepare to be iterated.
Pizza, thank you very much for the follow. Much appreciated. That'll also give me a couple of moments to write down a couple things. So when we're thinking about modern symmetric ciphers, we have two different classes that we're working with. We're working with classes of block ciphers and classes of stream ciphers. So block ciphers tend to do all of their encryption via blocks. That's kind of the idea of where the name came from. So let's just maybe jot that down. So block ciphers. So the idea is they'll encrypt one block, they'll move on to the next block, they'll move on to the next block, they'll move on to the next block. Stream ciphers are a little bit different. They tend to go bit by bit. So we're going to take a look at a block cipher, which is called the Data Encryption Standard. So basically what's going to happen here is we're looking at blocks of bits, and we're encoding the data using these blocks. So when it comes to kind of modern encryption, what we want to be able to do is cause confusion and diffusion in the data that we're trying to protect. And the way that block ciphers do that is through a process called permutation and substitution. We'll take a look at a small example of some S boxes today. So there are things called S boxes or substitution boxes, and things called P boxes, which are permutation boxes. And these are often, I guess, algorithms that are set up in advance of working on one of these ciphers, where we would, pass some information into this box. It's a function that kind of takes an input and gives us back an output, and they're kind of preloaded typically into the algorithmic process. But the key here is that these boxes are designed to cause some of the things that we want, which are confusion and diffusion. So in other words, we want to make the process of encrypting the data relatively tricky to figure out how to do, and we also want that end product to not really share a strong resemblance with what the input looked like. Archimedes, yeah, welcome in. Yeah, this is going to be a bit more about number theory today. Hey, Beldam, how's it going? Welcome in. Yeah, we're looking at some advanced cryptography today. So my apologies. I had to record some videos for a class. We're going to be doing that in place of our math contest questions today, although we will be back next Wednesday with math contest questions. Or if we have some time later today, we might tackle one or two, but I do have to tutor a little bit later today too. So as of when I wrote my notes, there were two major types of block ciphers. The first one's called a Feistel network. That was weird. Which is what we're going to be looking at today. So DES is a type of Feistel network. And then there's also substitution permutation networks as well, which I'm not as familiar with. Now, what I do know about Feistel networks is they typically have kind of this process of taking the information, breaking it up into blocks, and they go through kind of this function process, this function XOR process, where the blocks on the left and right side go through the process and they end up getting like switched around. So during every stage of the process, the outputs get flipped until we're done the full process. And Feistel is, the Feistel network is named after the inventor. So I haven't actually looked up, what's his name? Horst, I think. Horst Feistel. So we can take a look at roughly the dates that they were doing their work. So they were clear in the 20th century, so born in 1915, died in 1980. So actually did their work before I was even born. Worked on the design of ciphers at IBM. So pretty cool backstory. Culminated in DES, right? So Horst Feistel laid the groundwork, I would say, for the Data Encryption Standard. So did a lot of work there. So German in nature. So congrats to those of you who have German ancestry. We are celebrating a lovely German mathematician today. So before we move into the process of DES and like what a Feistel network actually looks like, one other preliminary thing that might be helpful to know is about cryptographic keys. So when we're working with block ciphers, we have two different kinds of keys. We have a cipher key and a round key. Now, the main cipher key is going to work how we probably suspect it to work. It's the key that's generated in advance of going through the algorithm. It's going to be the one that's shared between the two parties that are looking to protect that data and share that data. But the round key is something a little bit new and different. So our round key, so when we get into the process of the Feistel network, we basically go through a bunch of rounds in the Feistel network, and each round requires its own key in order to go through the function process, the XOR process. So depending on the Feistel network we're using, there's going to be some kind of key generation schedule. At least that's the case in DES. We start with maybe the cipher key, for example, and we go through this process of creating what are called round keys. So for each round of this network or each round of this process, we have a new key that we're using to do some of the XOR processing that we need. Okay, so we have a key schedule. It's going to generate what we call round keys. And basically what we're doing here is just saving a little bit of time in processing, and probably processing power. So we don't need to, in DES we're going through 16 rounds, so we could either pre-generate 16 keys to be shared between the individuals, or we could just use the cipher key, create a bunch of round keys as a derivative of that cipher key, and that saves a little bit of processing power, I would assume. And so the idea is, as long as each individual has the cipher key and each individual knows the key schedule, they would have access to all of the keys so that if they needed to do this process in reverse, they could. Alrighty, so that gives you a little bit of a background on some of the fundamental pieces that we need in order to go through the process. Let's take a look at what a Feistel network does. And then we can take a more kind of broad stroke approach to looking at what DES does, and we'll take a look at a smaller example too, so we can kind of work through the process with some smaller bits. So for a Feistel network, like I said, it was named after Horst Feistel. Who was that individual that did a bit of work with IBM. So he's the one that laid the groundwork for DES for us. And most block ciphers use one of these networks. So let's take a little look at how this might be set up and kind of what the general procedure looks like for working our way through a Feistel network. So what we do is we start with our plain text message.
Brace yourselves, everyone.
So getting back to it, if we have our plain text message, what the Feistel network is going to do is it's going to go through an initialization phase where it divides this plain text, it divides these bits in some kind of way. So it varies by network to network, but in broad strokes, let's just say it divides it into a left side and a right side, which we're going to call R0 and L0. And that's really just kind of the idea for initialization. We just divide into two parts. So when we go through this initialization phase and divide up the initial plain text message, this could be done evenly. So I could be taking an even number of bits to the left side and the right side. Or it could be uneven. It just depends on the particular network that we're working with. For DES, when we look at the Feistel network for DES, this division is equal. So we have the same number of bits on either side. So once we go through the initialization phase, then we start working our way through the different rounds. So for example, round 1, it's kind of like a boxing match or something. Round one. In round one, uses key 1. So remember, in the background, what we've done is we've maybe taken our cipher key, we've developed a key schedule, and whatever that first round key is in the key schedule, we're going to grab that and use it here in round number 1.
Art's cute, but I'm a Zeta cool singularity. Get too close and you'll spaghetti fight. Keep up, player. 3.4159. Yes!
So, getting back into it, friends. Key 1 goes through some kind of function with R naught, and the output of that round key with R naught going through that function is often XORed with the left-hand side. So what we're going to do is we're just going to basically go through a XOR process, if I can spell XOR correctly. So this is an exclusive OR process. And then everything switches. So the output that I get from L naught and going through that XOR process, now that becomes the new R1. And then R naught becomes the new L1. So that would be the completion of round number 1. So that's the basic setup. Round 1 uses key 2, round 2 uses key 2, and we just keep going until we're through all the number of rounds that we need. So round 2 uses key 2. And so our round key 2 is going to be applied to R1. And then after that's done, we XOR with L1. So we just keep going through this process. So this goes through some function. We pass it along over here to be XORed with L1. And then we just keep flipping these around. So the output of that becomes now our new R2, and then R1 becomes our new L2. So this just keeps on going until we're done. Boop, boop, boop. And then suppose it goes through n rounds. So once we're done, we're going to have an Rn and an Ln. And then we just swap these to get the ciphertext. So we basically just do something that's kind of like this. Boop, and then we get the bits that we need for the ciphertext. So hopefully that gives you kind of an idea of what the Feistel network does. It's just basically a large process. There are some sub-functions that are at work here. The key schedule is required here to develop the round keys that we use as inputs for some of these sub-functions. And you just go through a bunch of different rounds. For example, DES is going to go through 16 of these rounds before we land on the bits that we need for the ciphertext. So let's move into le pièce de résistance, which is the Data Encryption Standard, or DES for short. As I was saying before, definitely outdated now. But it used to be the pinnacle. And the reason why we typically don't use DES anymore is the key size. So the cipher key, I believe, is 56 bits, which to today's standard is just considered too small. It's probably too easy to do an attack on a key size that's that big. DES is a Feistel network. And we have 16 rounds. And during each round, we use a 48-bit round key. Now, you might think to yourself, that feels weird. If the initial key size is 56, that means we're going to lose some amount of bits when we go into the key schedule. And that feels weird, right? If I got a XOR stuff, how do I XOR two things that are of different size? And I think that's a good question to ask. So we will answer that question along the way. Okay. Blah, 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 nobody cares. And I guess the overall goal here is that we're going to encrypt data in blocks of 64 bits. Okay, so that's why it's called a block cipher, because we're actually taking blocks of 64 and we're encrypting those one at a time. All right, so let's move into the kind of step-by-step procedure of what the DES algorithm looks like. Step one, we call the initialization phase. We're basically getting everything ready to go for the 16 rounds of the Feistel network. So what we need to do is we need to take our plain text and we need to break this up into 64-bit chunks because we want to input that into our block cipher. So we just break this up. If our plain text has more than 64 bits, well, we're just going to break it up into chunks of 64. If the amount of bits is not divisible by 64, my guess is that we just add some padding at the end. I'm not sure exactly what that padding might look like. Maybe it's just a bunch of zeros, maybe it's a bunch of ones, I'm not really sure. But we probably just add some padding at the end to ensure that we're divisible by 64. So what we're going to do is we're going to take one of those 64-bit chunks. I'm just going to represent each bit with a number. And the idea is there's an initial P box that we go through. So let's say I have my 64 bits. There's going to be a P box that this passes through. Now, I don't know if I have quick access to that, but I can show it up on my personal camera. So I know that it should be available for my students, but the idea is there's like a P box. It's going to look like this. It's going to take the initial 64 bits and it's going to rearrange them in a particular way. So for example, bit 58 will become the first bit of the new thing. So just for funsies, maybe in green is going to be the new 64 bits that we have, the new 64 zeros and ones. But this first bit that I have after going through the P box is really the original bit 58. The second bit that I have is really the original bit 50, the original bit 42, and so on and so on. So in red here is just showing you the initial bit. Okay, so that's the idea with each of these 64-bit chunks. They get rearranged by this P box. And then to finish off the initialization process, we just bust this into R naught and L naught. So we're basically just breaking this up and saying, okay, the left side is going to get whatever comes out of the first 32 bits, and then R naught is going to get whatever is left over. So from bit 34 up to bit 64. Oops, that's not right. Try again. From bit 33, I should say, up to bit 64. So we're just gonna, so DES breaks those 64 bits exactly in half and puts 32 bits on either side for the remainder of the process. Now remember that depending on the Feistel network, this doesn't have to happen evenly. It could be an uneven break of bits here, but for DES it is even. So step 2 is still kind of like the to me it still feels like part of the initialization phase. But let's just think about it separately for now, just to kind of compartmentalize a little bit. What we need to do in step 2 is actually generate all of our round keys. So we're going to take our original cipher key, we're going to develop some kind of schedule, we call it a key schedule, and we're going to generate all of the keys that we need for each round, all of our K1, K2 up to K16. Okay, so we take the original cipher key, we're going to create 16 round keys, one for each round of the Feistel network, and, oh, this is a bit weird. I'm trying to remember how this one... Yeah, we have to compress and permute here. So each of these keys has to be 48 bits. So how does that happen? So what we do is we split the 56-bit key into 28-bit subkeys, or 28-bit parts, I guess. Not subkeys. So I'll give you an idea of maybe how the key schedule might work here. And when we go through a specific example later, we can actually develop these keys together. So there's some kind of process for how we create the keys. And for DES, we take our original 56-bit key, and we divide it up and we perform some shift lefts of the bits. So for round 0, we don't really do anything. This is actually just our cipher key. But as soon as we hit round 1, we do a shift left of the bits by 1. I'm going to go to a couple of more exciting ones. So by round like 4 and 5, we're doing shift left. We're shifting left by 2 bits. And until we get to round 16. Round 16 is a shift left by 1 bit. This key schedule is posted online, so if you did want to see the full key schedule, you could go look it up. It is publicly available knowledge, but this is our key schedule. And so the idea is we take our original 56 bits, we are breaking them up into 2 kind of 28 sub-bits on either side. And then we do some kind of shifting to the left. So what's happening is we're potentially moving bits in this direction. So any bit that would be, say, like the leading bit of that first 28-bit chunk, if I'm shifting left, it's going to actually land over at the far side of this second 28-bit chunk. So that's kind of the idea. So I'm never, even though I'm dividing into 28 sub-bits each, I'm not really losing the information from the original 56 bits. I can always kind of recapture that information by just knowing how many shifts I've done to the left and shifting to the right. Okay, so how do we reduce this down to 48 bits? Because once I do the shifting and I kind of attach these back together, I still have 56 bits. So, once the shift is done, we reattach to get 56 bits, and then we go through a compression permutation to reduce the number of bits here down to 48. So how we are selecting the 48 from the 56, that is not clear to me in the process, but it would be some kind of function. So we basically would say, hey, these are the 56 bits, so we're going to just stuff them into this function, and the output from that function, that compression box, is going to be 48 bits. So if you want to call it a C box, you can. But the idea is there should be some function that will return back what we want. Okay, so step 3, to me, is kind of the fun part. Okay, moving along to step number 3. So we have a block of 64 that's being broken down into blocks of 32. And now we have a round key that's coming in that's 48 bits. So we need to figure out how we're going to determine the difference, right? So if each of our blocks in R0 and L0 are 32 bits, and my round key is coming in at 48 bits, how do I bridge that gap between the number of bits so that I can do an exclusive OR operation? So that's the point of step 3. So just recall, all of the work is going to be happening on the right-hand side of the Feistel network. So right now we are stuck with 32 bits. So bits 33 up to bit 64. And the issue is that R0 is 32 bits. And our key 1 is going to be 48 bits. So here's what we do. We bust our R0 into blocks of 4. I'm being very careful to get my numbering correct here. So it would look something like this. And then we are going to expand this up in a very particular way in order to get up to 48. So let's kind of think about the process a little bit. So if I have 32 bits and I break it up into blocks of 4, I'm going to have 8 blocks of 4 right now. 8 blocks of 4. And I need to add 16. Is it going to be 8 plus 8? So in order to get us up to 48 bits, we need to add 16 more bits to our R0. So the idea is to take 2 bits from each of these blocks and add them to the current structure that we have in order to get up to the 48 bits, right? So currently I have 8 groups of 4. We want to turn this into 8 groups of 6. And we do that in the following way. So I'm going to write down the numbers, and then we'll take a look how we append or update the structure to get what we want. I feel like I'm going to run out of space very quickly here. But in red, let me just append how we're going to do this. So 64th bit will come along over here, and the 37th bit will come along over here. The 36th bit will come along over here, and we're going to pick up the 41st bit over here, and we're going to keep on doing this until I get the 60th bit over here, and then at the very end, we will also append bit 33. So we end up getting something that looks kind of like this. So the end bit of our block of 4 gets added to the start of the following block. And then the start of each one of our blocks gets appended to the end of the previous block. Right, so for example, this is the end of our last block. That would get appended to the start of the next block. This is the start of our first block. That gets appended to the end of that previous block. Okay, so now we've gone from 8 blocks of 4 up to 8 blocks of 6. Happy days. That is not how you spell need. Okay, so once we have that, we can collapse all this back together. That's going to be our 48-bit updated R naught. And then we're going to XOR that with the key 1. Step number 4 is S-box, P-box time. So not too much to draw here, but the idea is the result of step 3 just passes through S-boxes and P-boxes just for some added security and confusion and diffusion. So the 48 bits from step 3. Divided into blocks of 6. And then they pass through S-box and a P-box. When we do our smaller numerical example, we'll actually create an S-box, and I'll show you that process of moving stuff through an S-box. For the DES, we have 48 bits. If we're breaking it up into blocks of 6, then we technically have 8 S-boxes that we're working with. I'll kind of show you what they look like. It's just some kind of like table like this, where you have to find the 6-bit block as input and then match it up with a specific output. So it's just some kind of fancy function that's going to take my input and substitute it with something else. That's all an S-box does. Our permutation box we've talked about already. It's going to look at the bits and then it's going to rewrite them in a specific kind of way. So it permutes the bits somehow. As a result of passing through the S-box and the P-box, we have an output that's 32 bits. So the substitution box can take larger bit chunks and break them down into smaller bit chunks. So the idea here is the S-boxes will take the 6 bits, will substitute them out for stuff that's of smaller size. So we're gonna go from 8 6-bit pieces down to 8 4-bit pieces again and have a 32-bit output. People want an Xbox. True. Where are the Xboxes? Oh, we've only seen S boxes, P boxes, and C boxes. I don't think I've ever seen it go further than an S box. Step 5 is what we call XOR and swap. So once we go through this process, so let's say we've started with our two initial 32-bit sizes here. Remember, R0 has already gone through the expansion permutation. After it goes through the expansion permutation, our round key comes in. And we go through that XOR process. Okay, once we're done that XOR process, we go through the S box, P box process. That's going to kind of shrink us back down to the correct size of 32 bits that we want. And then the final thing to do is we XOR this, or exclusive OR this with L0. And then we do a swappy swap. So this XOR process with L0 brings us to our new R1, and then the original R0 becomes the new L1. So that finishes off one round of the DES structure. So remember, I'm just maybe going to go back in green and kind of just note down the bit sizes that we have. So our original R0 and L0 are 32 bits. So for example, when I come down to this XOR process down here, I need to ensure that whatever gets inputted into this process is 32 bits. So that's why the S box and P boxes have to reduce the size of what we're working with. Our round key is 48 bits. So when I go through the expansion permutation process, I need to expand out the number of bits that I have so that I can do this exclusive OR here. Okay, so we're working with two pieces that are 48 bits. We pass them into the S box and P box. Our output is 32 bits. So that when we do this exclusive OR, we're Gucci. We are good to go. That gives us a result on either side that stays 32 bits each. So this process goes on 16 times in DES, and our end result is going to be L15, which is 32, and R15, which is also 32. Sorry, the labeling starts at 0. So I think after 16 passes, we'll be left with L15 and R15. And then we just smack them back together to get a 64-bit thing for the finalization process. So that's that. So we do this 15 more times. Okay, once we're happy with the Feistel network procedure here, and we've done that our full 16 times, wait a second. I think we actually do end up at L16 and R16, right? If L0 and R0 are the initialization, then L1 and R1 would be after round 1. So I do think we get to L16 and R16. I was just looking at my notes, and I think that makes sense to me. So we're actually counting the number of rounds that we do, so we should land on L16 and R16. We attach these together to get something that's 64 bits. Oh, my apologies. To get 64 bits, there is one final permutation, and then we get the ciphertext. So it's a big process, right? It's pretty intense. The inner workings of how DES works is quite challenging to follow. I remember when I first learned this, it took me quite a while to kind of figure out all of the moving parts and how things were working. And the crazy part is it's already really complicated. So you could imagine potentially how complicated encryption structures must be today. If this was outdated in what, the 80s, and how long has that been? That's been like, what, 40 years? 40, 50 years? Like, how advanced are we right now? Would be my question. So there's a lot of algorithms that I don't know, which I think is wild. I would like to work through a small example so you can get a feel for how that structure looks like. So let's just take a moment to just kind of take a small break here. We're going to talk about a small example. Where we're going to go through these 6 steps, but we're going to actually like assign some S boxes to some of these steps, and I'll show you kind of how the bits interact with each other, just to give you kind of a feel for how it works. So let's consider a plain text message. Our plain text message is 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1. And let's say we have a cipher key that looks something like this. We have 1, 0, 1, we have 1, 1, 0, and we have 1, 1, 1. So a couple things to note here. Our plain text message is coming in like blocks of 3. So we have what, 3, 6, 9, 12. So we have 12 bits here. And the cipher key is also coming in blocks of 3, but there's only 9 bits here. Okay, so that we already have a discrepancy between the key size and the plain text message. So we might have to do some kind of expansion if we need to do some Zoring. Another thing that we might want to consider here is if I do divide the plain text message in half, I get 6 bits and 6 bits, which again doesn't quite align with the 9 bits that we have for the key. So just a couple things to keep in mind. The sizes are going to be a little bit funky because we can't quite get them to align perfectly when we start the Feistel network process. Okay, so let's take step 1. Let's split our plain text into 2 sides. And let's do equal sized sides. So nice and easy, we'll keep L0 over here. That's going to be our first 6 bits, so 0, 1, 1, 1, 1, 0. And then R0 will be our second 6 bits, which will be 0, 0, 1, and 0, 1, 1. So step 2, we want to create a key schedule. Rather than making things overly complicated, I'm just going to say, like, let's start with the ith bit. And so the schedule, I said, let's start with the ith bit, and then we'll just add the next 7 to it so that we get a round key size that's 8 bits long. And you'll see why I'm doing this in a second. Okay, so if I want to form key I, right, or key 1, key 2, we'll have 8 rounds in ours if we do this kind of schedule. So maybe I'll write down the first couple keys. So for example, key 1 would be taking the first bit, which is 1 in the key, and then taking the next 7 bits. So 1, 1, 2, 3, 4, 5, 6, 7. So here's our key 1. If I wanted to take key 2, I don't know if that's behind my head. Nope. So key 2, I would start at bit 2, which is 0, and then write down the next 7 bits. So I have 1, 1, 1, 0, and then 1, 1, 1. So these would be the first 2 keys, for example. And I could do this for as many rounds as I want. Maybe we'll do this for, I don't know, 5 rounds, 4 rounds, doesn't really matter, right? We determine the number of rounds we want to do in our Feistel network, but let's just pretend this is how we generate the keys. If I have a 9-bit key, maybe I only do it twice, right? Maybe I say, okay, I stop after I hit the last bit, so maybe I'm only going to do 2 rounds. I don't know, right? There would be some kind of agreed upon structure for what this might look like. But this step is called, this is our key schedule step. Okay, so step 3 is where we start getting into the nitty-gritty of how the Feistel network works. So we want to do a comparison. So we want to compare the key size to R0, the size of R0. So R0 right now is, let's just maybe write it down, is 0, 0, 1, 0, 1, 1. So we have 6 bits. However, each of these keys is 8 bits. So if I wanted to do an exclusive OR process, which is usually what we do in this part of the Feistel network, we have to take R0 and we have to expand it a little bit. We have to expand it, in this case, by 2 bits in order to match everything up so that we can go through that XOR process. So that's what I'm noticing right away. So we need to expand R0 by 2 bits. So the question is, how do I do this? And again, it's going to be a pre-decided way of doing this. For DES, we kind of appended bits in a very particular way. And we're just going to do the same thing here. So let's just pretend that maybe we'll take R0, which is 0, 0, 1, 0, 1, 1. And we're going to expand it in the following way. We're going to say 0, 0, 1, 0, 1, 1. And in red, I'll just add some new bits. So let's put a 0 here and a 1 here. So let's do something like this. Okay, so here's the expansion process. And these bits can go anywhere, right? The important part of this process is seeing that there's a discrepancy in the size and developing a procedure to ensure that when we go into the exclusive OR process with K1, we have the number of bits that we need. So in our case, we have 8. Okay, so now we bring in our K1 key, which looks like this. So it's 1, 0, 1, 1, 1, 0, 1, 1, and we do our exclusive OR. So an exclusive OR only returns back the number 1 if one or the other of the bits is 1. So in this first column, I have a 0 and I have a 1, so exclusive OR returns back 1. In column 2, there are no bits that are on, so the exclusive OR returns back 0. In column 3, since both are on, and we're working with the exclusive OR operation, this actually turns into a 0. So I only ever get a 1 if only one of the bits is on. So our exclusive OR is going to return back to us something that looks like this. Step 4 is where we normally would go through S boxes and P boxes. We're going to skip the P box process here because I don't really want to develop a permutation box. But let's pretend that we create some S boxes. So what do I notice about this output from step 3? Well, it's 2 blocks of 4. Okay, so the output of step 3 is a 2 by 4, right? So I have 2 blocks of 4 bits each. As I move along the Feistel network process, I want to be able to exclusive OR with this with that left side. So remember, what we're trying to do is we're expanding and permuting. Then we're going through the S box, P box process. And then we want to exclusive OR with L naught. What's the size of our L naught? Well, it's 6 bits. So I need to take this 8-bit output and now use the S box to reduce it down back to 6 bits. Okay, it's 2 by 4. So we basically want each of these 4 bits to come out on the other side as blocks of 3. And then we would have the correct size to do the final step. Okay, so L naught is 2 by 3. So each S box that we create must reduce 4 bits down to 3. So how do we use our S boxes? Well, we're going to grab the 4-bit structure that we have as output from step 3. So we're going to input 1001 into S1. And I'll just highlight where we are in S1 so you can kind of see that process. So I start with bit 1, so I'm inside of this row. Okay, my first bit is a 1. My remaining 3 bits are 0, 0, 1. So now I'm in this particular column. So the intersection of row and column tells me what that output has to look like. So if I pass that first set through substitution box 1, my output is 1, 0, 0. And I do the same thing up here with this second 4-bit block. So I have 4 zeros. That one's going to go into substitution box 2, and same kind of story. So this tells me that I'm at the intersection of this row and this column. So here is the output I'm looking for from S2. All right, so we've basically taken our output from step 3. We've gone through the S box process, and we've been returned 1, 0, 0, 1, 0, 0. So step 5 is just to complete the process. And then we kind of determine if we want to go through this process more than one time. I would recommend trying to do one more round of this on your own, using the information that's been given to you. So how do we do the expansion? How do we go through the S-box process with the ones that are created? Maybe try doing one round on your own, and that should be enough to prepare you for something that you might see on the final exam. Okay, so step 5 for us is we want to XOR and swap. Okay, remember our L naught was 0, 1, 1, 1, 1, 0. R naught started at 0, 0, 1, 0, 1, 1. So we went through the expansion permutation. Where K1 kind of came in and we did this XOR process. Now, all of that was done in previous steps, and then our output went through the S boxes. And so now we're doing this final process of the XOR and swap. So our output was, what was it? It was 1, 0, 0, 1, 0, 0. That was the output from the right-hand side process. Now we have to drop our left-hand side down and do that exclusive OR one more time. Okay, so we're going to XOR these together and then finalize round number 1. Okay, so we should get 1, 1, 1, 0, 1, 0. So this becomes our new R1. And then the old R0 actually becomes the new L1. So 0, 0, 1, 0, 1, 1. And there we go. So that's one round using a smaller example. If we want this process to keep going, we can do this for as many rounds as we want. We just have to make sure that we understand what that key schedule looks like. If we want to do maybe more than two rounds, like are we going to kind of repeat and cycle back through previous bits, or do we do something else? But we did create 2 keys in the key schedule, so my recommendation to you is to now take the outputs that we have, the L1 and the R1, see if you can go through that process again using the 2 S boxes that we made, and using key 2 to do the expansion permutation process. Okay, so I'm just going to kind of jot down some notes here so the process would repeat as much as we want. Maybe try round 2 on your own. All right, so let's just do some concluding statements here. So that's maybe a numerical example just for your reference in case you just want to see what some of those pieces look like. Just a couple notes here. DES is publicly available. We did see a pseudocode of it on Wikipedia. So you should be able to search up. You can probably go into like ChatGPT, Claude, say, hey, code me up something that's really close to what DES looks like. You can explore that code on your own if that's something that is of interest to you and is something that you want to do. And while it doesn't look like it, like as we work through one of these examples, the algorithm is actually reversible. It doesn't look like it. But if you use the round keys in reverse order, it works. We can decrypt and get back to the plain text message. So the key to using DES effectively was that the individuals sharing information, they were the only ones in charge of the cipher key, right? So inputting the cipher key into the key schedule produces the 16 rounds that we need, the round keys for DES. If we, I guess, reverse the process, starting with round key 16, working our way back up to round key 1, then we theoretically should be able to undo any encryption that has happened by just doing everything in reverse, which is kind of cool, actually. Originally, the strength was in the key size, so that's why it was so effective in early on computing. Now, this is so funny, because since we're working in bits, this gave us about 2 to the power of 56 different possible keys. And to think about how big that is, this is about 72 quadrillion possible keys. And the crazy part is 72 quadrillion possible keys is not strong enough in today's standards. I think that's the most fascinating part, is just like how strong an algorithm has to be in today's standard. So if we were doing, I just want to give some historical context here. So in 1998, DES was cracked in about 56 hours. By 1999, they had it down to about 22 hours. Which is kind of wild. And by 2008, the average time was less than a day. So put that in perspective, right? So current computers, like my NVIDIA, what is it, 3060 or whatever, can crack DES in less than a day if I just let it chug along. It can go through all of the 72 quadrillion possible keys and decrypt your message in less than 1 day. That's wild. I assume that the 1998 and the 1999 hours were special cases, like where like maybe a particular computer was able to do it in that particular time. But where we really see kind of the baselines shifting was in that kind of early 2000s, right? The average computer now has a pretty good GPU processor, can probably actually crack this in less than a day. So to me, that's kind of wild. So what did they do? In 1999, since the average time was starting to get pulled down quite a bit, so by 1999, they invented what's called 3DES. And then by 2001, we moved over to the Advanced Encryption Standard, which is AES. So yeah, so kind of wild. I think when I started writing the notes, like, I have a note here that says like, by 2016, if you have an NVIDIA 1080 GPU unit, you can crack it in 2 to 15 days, which is kind of crazy to me, right? Like, it's kind of wild how many different possible keys you can churn through and just doing a brute force attack.